How's it going, everybody? This video is a part of a series of questions for the binary search algorithm. In this video, we will look into solving the question of finding an element in a sorted array. Say we are given an array 1, 0, 3, 5, 9, and 12. We want to find the target in that particular array and return its index. And if the target is not present, then we'll return -1. Say here 9. 9 is at the index 4, so we return 4. And target 2 is not present in this array, so we return -1. We can do a linear search by looping through the array and check if the element is present in the array or not. And if it is present, then we can return the index, and if not, then we return -1. So what is the complexity of this algorithm? Since we are looping through the array, the time taken is proportional to the length of the array. So the time complexity is O of n, and the space complexity is O of 1 since we are not using any additional space. Is there a way that we can do better than O of n? Since the array is sorted, we can use binary search to find the element in this array. To solve this problem using binary search, let's let's consider two pointers, one at the start of the array called start and another one at the end of the array called end. So using this formula, we can compute the middle pointer. Start is at 0, the end is at 5. So 0 plus 5 is 5, and we divide it by 2, it's 2.5. And we consider the floor, this is the sign for the floor. So we consider the floor of 2.5, and that is 2. So the middle element is at 3. So if we compare the middle element with the target, we have three different cases. The first case is if the middle element is equal to the target, then we have found our element, then we can straight away return the mid. In our situation, so we know that 3 is less than 9. And because this is a sorted array, all the elements before 3 will also be less than 9. So this means that if 9 is in the array, it has to be on the right hand side of the mid. So we can straight away discard mid and all the elements that are there on the left hand side of the array. If mid is less than the target, which is our situation right now, discard the left part of the array and reconsider only the remaining elements. So you move the start pointer one element ahead of the mid. So now we have a different subset of the array that starts at index 3 and the end pointer is at index 5. We recompute the mid using the same formula that we have here. Uh, so we have 3 plus 5 divided by 2. 3 plus 5 is 8, divided by 2 is 4. Middle pointer is at index 4. We compare the middle element to the target. Since they both are the same, we straight away return 4 and we conclude the problem. Let's consider another problem. Here the target is 2. Like the previous problem, we have two pointers, one pointing at the start of the array and another one pointing at the end of the array, the start and the end. And we compute the mid over here using the same formula as above. The mid, so it's 0 plus 5 divided by 2 is 2.5, and we take the floor of that, so that is true 2. So our middle element is at index 2, and we compare the middle element 3 with our target 2. In our case, the middle element is greater than the target. This means that all the other elements after the middle element will also be greater than 2 since the array is sorted, so we can straight away discard the remaining part of the array. So this particular situation is equivalent to our second case where the middle element is greater than the target. So we discard the right hand side of the array, and to discard the right hand side of the array, we bring the end pointer to an element before the mid pointer. So that is, so the end becomes mid minus 1. So now we have reduced our problem to a smaller subsection of the array. Now we repeat the same process again, where we find the mid. So here it's 0 plus 1, that is 1, divide by 2 is 0.5, and we take the floor, that is 0. So our middle element is at 0, and we compare the middle element with the target again. So minus 1 is less than 2. So this is the third case where we move the start pointer one element ahead of the mid pointer. So that is, the new start becomes mid plus 1, mid is 0, the new start becomes 1. So we perform the same process again, where the start is at 1, the end is also at 1, so it's 1 plus 1 is 2, divided by 2 is 1. So the middle element is also at 1. Now we compare the middle element, that is 0, with the target. Since 0 is less than target, so we discard the right hand side of the array and we move left. So this is the start pointer. The mid was also over here. Mid is also here. The end pointer becomes here. This means that we have no array to divide anymore. Since we don't have any array to divide anymore, this means that 2 doesn't exist in the array. And in this situation, we return minus 1. So in binary search, in iteratively at every step, we divide the array into half. So say if we have a size of say 128, in the next iteration we divide it to 64, then in the next iteration we divide it into 32, and so on, all the way up until we either find the element, or we don't have, or the size of the array is 0, which means that we cannot divide it anymore. So the time taken to complete this process is is proportional to the log of the size of the array. So the time complexity for binary search is O of log of n, and since we are not using any additional space, the space complexity is O of 1. Let's write the code for the algorithm. I'll write the code in Python and provide the links to the code in JavaScript and Python. Even if you're not familiar with Python, I'd highly recommend sticking to the video, because once you understand the basic structure, it will be fairly easy to write the code in any other language. So let's get started. Here I've defined a basic skeleton with the input examples, and we'll write our code here. First, we'll initialize two pointers pointing to the start and the end of the array, that is start and end. The while loop will iteratively keep dividing the array until the start pointer becomes greater than the end pointer, in which case the while loop will terminate. In every iteration, we'll compute the middle pointer, that is mid is start plus end. We'll use the floor division. This operator in Python is a floor division operator. If the element at the middle pointer is equal to the target, then we return the middle element. In our situation, this is the case 1 where we found the target. Else, if the middle element is greater than the target, and in our situation this is the case too. So where we bring the end pointer to an element before the mid pointer, so the new end becomes mid minus 1. Else, in the third case, the middle element is less than the target, then we move the start element to an element greater than the middle pointer. Eventually we return minus 1 if the end pointer becomes greater than the start pointer and we still haven't found the target element. So in that situation we return minus 1. Let me know your thoughts in the comment section. I hope this video was helpful, and if it was, then please like, share and subscribe. Thank you.